Welcome back. This is Larry Benko W0QE, and I suspect most everybody is familiar with the 50 or 60 Hz auto transformer, which is also known by various trade names such as Variac or PowerStat. SimSmith is uniquely suited to analyzing and displaying exactly how the auto transformer works, both at 50 and 60 Hz and at RF, which will be another video. For this video, I will use the terms auto transformer and Variac interchangeably. A couple of months ago, I read a forum post where a guy burned up a few Variacs, even though they were properly fused. I think it would be useful to fully understand how a Variac works with some help from SimSmith. Shown here are a couple pictures of the same Variac, which has 5 terminals which we can use to achieve the operation that we want to have the Variac achieve. The Variac allows the shaft of the Variac, which turns the wiper, to be either mounted in a way where it comes out of the top of the Variac or the bottom of the Variac. And consequently, we have an operation you could call counterclockwise or clockwise based on which way the shaft comes out of the Variac. In this case, I've got the neutral connection, or the common connection, connected to terminal 2, which is one end of the winding. I have the hot, which is 115 volts in this case, brought in right here on terminal number 5. Now, as the wiper would go from the most clockwise position, which would be 0 volts, counterclockwise to here, the voltage at the output would go from 0 to 115 volts, and then if we continued moving the wiper up to here, it would go all the way up to 135 volts. So this Variac can be thought of as being a step-down and a slight step-up Variac at the same time. This one over here is shown with the shaft coming out in the other direction, so we mount the neutral or the common on terminal 4. We put the mains input, which is 115 volts, on terminal 2 up here. And now in a clockwise direction, we go from 0 volts up to the full voltage, which is 115. Some small Variacs only have 3 terminals because these taps are pretty hard to make on very small winding wires that are used in small Variacs. But I've seen various arrangements where they have 4 terminals where you don't have the shaft coming out possibly on both sides. But anyways, this is just an idea of how to connect the Variac. Let's move on and see what SimSmith can do to help us understand how it works. What I plan on doing here is to take SimSmith and create a circuit which simulates a Variac, and then I intend to look at the currents associated with the Variac for various values of load and various values of the knob setting on the Variac, which gives us the voltage. And let's do that. The first thing we're going to do is change the frequency from 10 megahertz to 60 micro megahertz. 60 micro megahertz is 60 hertz, of course. We're going to change the generator type since it's a 120 volt application. The source impedance is very low, so let's make it an absolute voltage type. And have it set to parameter A is just fine. We could put a voltage number directly in here also. It wouldn't matter. We'll leave it this way. And I come down here and I'll come down here and I'll set that to be 120. So now I have a 120 volt generator to deliver 120 volts to the load, no matter what the load impedance is. And we see 120 volts at the load here. And as we see as I change the load impedance, the load voltage remains at 120 volts. Of course, the current changes based on the resistance here, but the value still remains 120 volts, indicating we have a 120 volt source. So now the next thing let's do is put an auto transformer in here. And the auto transformer is one of 3 models that we can pick within the transformer. The first one we get by default when we drag the component up here to the circuit is a coupled transformer, as shown in the schematic here. Second one is another version of the coupled transformer where we define it by turns ratio and rather than 2 inductances. And finally, we have the auto transformer. I measured a 10 amp Variac and I measured a 6 amp Variac. And the numbers for inductance were somewhere between 3 and 4 henries. So let's just use 4 henries for that. And that's the right side inductance. So L sub R is the inductance on the right side of this component looking towards the left when the load out here is removed or is open. And likewise, L sub L, which is the left side inductance, is the inductance looking towards the right with the right side open. And as we see with the tap position here, which is indicated pretty accurately in SimSmith, as we change the inductance value looking at from the left side, we see the tap voltage changing. Let's just set that to 1 henry for the moment. So now what we have is we have a center tap with the coefficient of coupling of 1, inductance is proportional to the turns squared, and half the turns is 1/4 the inductance, and 1 Henry versus 4 Henries. All looks good. Now what I want to do is I want to sweep, rather than sweeping with frequency like we usually do in SimSmith, I'm going to sweep with the position or with the inductance from the left side. So it's equivalent to turning the knob. So the sweep will be, in the square chart, will be with the knob being turned in the Variac. So to do that, I'll pick this variable to sweep. I'll set this to be from, I don't know, something like maybe 0.1 to say 3. Doesn't matter what it is right now for the moment. I'll set that to be sweep. I can leave this this sweep value in here. It's not enabled, or I can hold the control key down and just get rid of it, or I could drag it to the trash can. All those are the same. And I have to select, of course, this 3 to take. Now I'll come over here and set this to be a sweep value. And what we see is it really doesn't matter. This impedance right here just changes what we see on the Smith chart. We're not going to use the Smith chart anyways in a few moments. But what I wanted to show here is, as soon as I touch this component, the sweep no longer works. There's a bug in all versions of SimSmith, I believe, up to through the current version. I have a new version, a beta version I'm going to use for this video. But if you've ever encountered this, the sweep does not work properly for the auto transformer when sweeping the component, the values for the two parameters, L sub R and L sub L. Now, if I go back to a coupled transformer, I get the sweep that's appropriate. When I go back to the auto transformer, it does not sweep again. So fast forward a few moments here. And now I have a new version, 16.8N. And version 16.8, or whether it ends up being 16.8 or 16.9 or 17 or whatever, has a lot of new features in it. And I'm not going to use any of those features for this video. But the primary feature, the only feature I'm going to use, is the fact that the sweep now works properly. And there's the sweep that's done properly. So from now on, we won't use this version. I'm sorry about the fact that the other version is not available yet, but I suspect it'll be fairly soon. The new version has features that aren't quite completely debugged, I guess, which is why it hasn't been released. But we can use this. We can use this for this video. And what I see here is a couple things. I see the two values of inductance being what I specified, and SimSmith gives me two other values. It gives me an upper value inductance and a lower value inductance. The upper value inductance is 1 Henry. 1 Henry down here. If a coefficient of coupling is 1, that becomes 4 Henries together. And if I change the value of the coefficient of coupling between these two coils, it looks like one winding, but we can think of it as one coil and another coil. What we see, other than the fact that the impedance changes, we see that the inductance on the top side changes value. You might think of it as being, well, it really can't change value, but it does. And let's examine that a little bit more closely. Shown in this circuit is something I do quite often in SimSmith, and it's a very powerful feature. And that is to create two independent circuits that I can compare. And we do that by adding a block in the middle, and you can add multiple blocks and compare more than two circuits if you wish. But the block in the middle clones the load here, and it clones this generator there by having this construct for the load generator block. You don't need to have them cloned. You can easily have this generator be different than this generator, but in this case I want them both to be identical, both load and generator. And this is the block that SimSmith gives us for the auto transformer. Same auto transformer we had before. In this case, I've set the coefficient of coupling to be 0.6. SimSmith calculates the upper inductance to be 1.52 Henries, the lower to be 1 Henry exactly. And what I do is build my own circuit and see if I can come up with the same input impedance, through gain, etc. for various values of coefficient of coupling and in the inductances here, and we'll see what happens. So the first thing I need to do is come up with a model. The model for coefficient of coupling is pretty straightforward, and that says that for a given coil with a coefficient of coupling K part of the coil, and remember K is a number between 0 and 1, so somewhere between 0 and 100% of the inductance completely couples to the other coil with the same factor again. They don't need to be the same inductance, but the same factor. So in this case, I'm going to build a circuit which is comprised of 4 coils. L1A and L1B together give us 1.52 henries, and L2A and L2B give us 1 henry. So I start off by copying K, the upper value, the lower value, from component A. And I do that right here. I copy those. And then I set the values for these 4 inductances. The upper inductance that's leakage is 1 minus K of the value that Sim-Smith says it's supposed to be. The coupled value is K times that upper value. And then the lower value, same thing. Now I have the value set for all 4 of these inductances, and I completely couple this inductor and this inductor with a coefficient of coupling of 1. When I do that, I see a couple things. We can close this off now. Let's get rid of this. Impedance-wise, what I see, and remember that 50 ohms here doesn't matter. All it does is set the center point of our Smith chart. What I'm looking at is the fact that I've got 2 curves here. The blue curve is what Sim-Smith says the impedance is. So we see it starting at 12 ohms and going to some value over here, which is 36 plus J368. And my circuit does the same thing. Remember, all ruse blocks do not follow some kind of a nice curve contour, but the ruse block just gives you a straight line without regard to what components are actually in it. So I have the same impedance, and you can vary the coefficient of coupling. You see the 2 of them still continue to track, just like you would expect, or you would hope. And we see that the output power, 3.82 watts, is the same in both of them. I change the coefficient of coupling, it's the same power. And I can change things like the tap point, move the tap point around. Again, same impedance for both of them, same power, 12.7 for both, same voltage, same current, everything's the same. So my model represents exactly what Sim-Smith is doing. The Q of these inductors may not match the Q of the inductors here. There's nothing that Sim-Smith allows us to do to set the Q. The Q is assumed to be what I believe to be 1 million. I don't know if the leakage inductance piece of this is also the same Q or not. It's hard to see the difference between Q of 1 million and Q of infinite. But nevertheless, my model models it extremely well. And that gives us a lot of confidence that what Sim-Smith did here was right, even though it looks kind of weird. It's the same, it's the correct circuit, and everything's good. So now let's proceed on and look at the currents. This is the same circuit we had just a moment ago, except offline I've added a few commands for plotting. I needed to do this not in the video because it takes a little while to get these to look nice in terms of what I was trying to show, so I did it offline. The first thing I'm going to plot is this command. Let's just look at this command by itself. RMS, which means I want to plot the RMS value with a stroke width of 5, and I'm going to label it A.PRI space V right down here, and it's going to actually plot A.capital V. A.capital V is the voltage from here to here on the right side of the A block. And if we plot that, we see exactly what we would expect, and that's 120 volts. By the way, we're sweeping with HL. HL is the left side inductance here, which is basically moving the tap up and down. Not linearly, but linearly with inductance. We'll fix that in a little bit. The next thing let's plot is the secondary voltage. Same mechanism as before, labeling it secondary voltage, and we're plotting L.capital V, which is the voltage right here to ground, which again is the output of the auto transformer. So we look at that one, we see it's nonlinear, but we see it goes from 0 volts when the inductance is 0, up to 120 volts when the inductance is 4, which is the value that the right side inductor is. And if we go beyond 4, what we see is, let's just do that. So they're at 4. If we go above 4, we see the model change up here, and we see it's now a step-up transformer. So back to 1 again for the moment. Next thing let's plot is we have to be a little bit careful here about how we plot some of these things, but we're going to plot the 2 currents, and we can plot those directly too. The current for the primary side is the same as the voltage, except instead of being A dot V, it's A dot capital I. So the primary voltage is right there. And the primary voltage you would expect to rise as you increase the inductance because we're putting more power into the output. We can see the power going into the output is 300 watts here. If we change the inductance values, we see the power rising. Well, if the power rises, then clearly the current has to be rising. The next thing let's do is let's look at the secondary current. The secondary current is, again, just what we had before, which was it'll be L dot capital I, which is the current going into the load. So let's look at that too now. Again, it's an orange trace now. And now we have two more currents to plot. And those are the only two currents that really count. And that is the current in the upper inductor and the current in the lower inductor. We can fix the problems with the current in the primary and the current in the secondary by increasing the wire size that goes to the Variac. But we can't increase the wire diameter of the actual inductors. So these are the two currents that we really have to worry about if we're concerned about protecting the Variac from burning up. So the current in the upper inductor for a step-down Variac will be the primary current. So I ask the question here, if the right side inductance is greater than or equal to the left side inductance, and if that's true, then it's a step-down transformer. In that case, then the upper current is going to equal A dot I, which was the primary current. Likewise, if we have the transformer acting as a step-up transformer, then the upper current is the secondary current. And that secondary current was just L dot I from before. In all cases, the lower current is the difference between the primary current and the secondary current. There's a node here, and the sum of the currents at any node is equal to 0. So the current coming in from the primary, the current leaving from the secondary, the current down here, they have to sum to be 0. So we can get that value for the current by just subtracting A dot capital I minus capital L dot capital I and plotting that. Now, if you're a little bit squeamish about that being the correct value, let's do something real quickly. And remember, my model is only good for a step-down transformer. So let's set the inductance to be something like 2 Henries. And let's look at the inductance in the upper matches the primary current. And as long as from this point on down, it is a step-down transformer. From this point on up, it's a step-up transformer. So the current here, the upper current matches the primary current. The lower current is the difference between the primary current and the secondary current. And if this is the trace, you might be a little bit concerned about how I calculated this. So I calculated it for my model. Now, my model is only good from this point here left, where the Variac is acting like a step-down transformer. But if we calculate that, and that is simply B, which is the component, dot L2B, which is this component right down here, and it's the current there. It's the current through that component. And since it's through that component, it's a small I. We're plotting it on the y-axis again, and let's plot it. And we see that that does match this curve exactly until it becomes a step-up transformer, in which case my model fails. So we're almost done. The last thing I want to do is make these lines straight, and I want this bottom to be equivalent to voltage. So let's do that now. And one final Sim-Smith circuit. I took this stuff that was plotted in the plot block before, and I moved it over to the D block. It's the same plotting we had just a moment ago, except instead of controlling this by the left side inductance, I wrote a little formula here. And this is true only if the coefficient of coupling is close to 1, but the dial, which is what the indicating dial, and it's going to go between 0 and 140 volts, and that's going to be the secondary voltage. The dial divided by G dot A, which is 120, squared times H sub R is the left side inductance. Doing that, and that's pretty much all we're done. All there is to it. I did add a little check in here to say if the dial was less than 0 to set it to 0, if it's more than 140 to set it to 140. Otherwise, the plotting is exactly what I just had a moment ago. So now what we end up with are straight lines for the output voltage versus the horizontal axis. And the output voltage is this voltage right here, and we can just adjust it and look at where the circles are. So if the control is set to 60 volts, that's half the voltage. And at 60 volts, what do we see? We see the primary voltage is at 120 volts. We see the secondary voltage at 60 volts. We see the primary current, which is green down here, at 2.5 amps. And we see the secondary current, which is orange, at 5 amps. So 120 volts times 2.5 amps is 300 watts in, and 60 volts and 5 amps is 300 watts out. We see our 300 watts right there. Everything's good. And we can move around. Now, what's going to happen? What we're worried about is having either the dotted black or the dotted gray line get above 10 amps. Because if that happens, then we burn up the Variac. So if this Variac is rated at 10 amps and we run it in the step-up mode, once we get up here with a 12 ohm load, we will have current on the green trace, which is the primary current, higher than 10 amps. But we also have this current right here, which is the upper current being slightly higher too. So 10.4 amps. Now, maybe that's within the realm of what we can do with the Variac, and that's just a little bit above. But we really should drop, if we want to run it in this mode, we really should drop this current, this resistance, increase the resistance enough that the dotted black line stops at 10 amps. Right about there's about where we need to be. So we see right here. May not be able to get right on it. I probably can't. Anyways, it's there, 9.99 amps. So 14 ohms is the smallest resistance we can have and be universally safe no matter what we do. Now, what happens a lot of times in a Variac is people are running the Variac down here at some lower value. Let's go back to 60 volts again, because it's a nice value. But they say at 60 volts, they drop this resistance down. And as we drop this resistance down, we start to see the currents rise. We don't care that they're up here higher. We're operating it where the dots are. So what can we do down here? Well, we're seeing the secondary current rise here, right there. At 6 ohms, the secondary current has exceeded 10 amps. If our fuse is in the primary line, which it must be, we must have a fuse here if the Variac is a standalone Variac, because some fault in here would allow a huge inrush of current from the mains, and that's not good. So for safety reasons, we want a fuse here. What can we do to protect the Variac? We are going to have to fuse the output side too. And then if we fuse the output or the input side and the input side both at 10 amps, we're safe to go. To respond to the poor person who made the comment on the forum, people were giving him all kinds of things, saying put the fuse in the tap. Well, if you put the fuse in the tap, then putting the fuse in the tap is by definition putting it in secondary. So we're only looking at the orange trace. And is that right or is that wrong? Well, it's not right when you run this up at 100 as a step-up transformer. And let's go back here to 12 ohms again. What we see is the primary current, which is green, is above the secondary current. So the primary current's too big, so you can't fuse the secondary and protect the primary completely. It's not too much of an overload, but it's 2 amps. You can't fuse the primary and protect the secondary, right? So we end up with needing 2 fuses. And we need a fuse in both the primary and the secondary, in which case then you've protected both the upper and lower windings. And this may be obvious to people. It's kind of a fun little experiment to have done. I kind of found it interesting to make Sim Smith do it, and I hope people have enjoyed it. If you've enjoyed it, let me know. Give me a like or something. Make a comment. If you'd like to see something done a little bit differently, let me know also.